Welcome to this new video about continuity. Here we're going to determine where each function is continuous. We're going to locate all points of discontinuity, if any, and discuss the behavior of the function f at these points. Let's start with the first one. The first function is f of x equals x cubed minus 5x, which is a polynomial function. And you have to know that a polynomial function is defined everywhere. It means on R, and it's also continuous everywhere. So here, the domain of continuity of this function is R. So easy, the domain of continuity of a polynomial function, any polynomial function is R. Okay? The next one is a rational function. Okay? And when you have a rational function, you have to know that it's defined where the denominator is not equal to 0 and it's continuous on its domain. So first of all, let's find the domain of this function. It's obvious that the domain of this function is the set of all real numbers except the points where the denominator is equal to 0. So you have to solve x plus 4 equals 0, and x plus 4 equals 0 means that x equals negative 4. So the domain of this function is the set of all real numbers except negative 4. We said that a rational function is continuous on its domain, so the domain of continuity will be the same. Domain of continuity of this rational function, domain of continuity is equal to R except the point negative 4. So the point of discontinuity is x equals negative 4. We're going to write discontinuity at x equals negative 4. And to describe the behavior of the function at this point, we have to compute the limit of this function at this point. So compute the limit of 3 over x plus 4 as x approaches negative 4, and you will find it's 3 over 0, and 3 over 0 is plus or negative infinity. I will not specify if it's plus or negative because it depends if it's negative 4 from the left or from the right. But anyway, we find an infinite limit, which means that we have a vertical asymptote. Good. Now we have to compute again. So to describe the behavior of this function at this point of discontinuity, which means that you have a horizontal, which means that you have a vertical asymptote at x equals negative 4. Good. To describe the behavior of the function at this point of discontinuity, we have to compute the limit as x approaches negative 4 of the function, which is 3 over x plus 4. It's equal to 3 over 0, and 3 over 0 gives plus or negative infinity, depending if it's to the left or to the right. But anyway, it's plus or negative infinity. I don't care, since I can conclude here that we have a vertical asymptote at this point. Okay, so the function will have a vertical asymptote at x equals 4, negative 4, sorry. Okay, now let's move to the next function. F of x equals, it's a piecewise defined function. It's f of x equals x squared if x less or equal than 2. It's equal to 2x if x is greater than 2. Okay, now the first function x squared, which is polynomial, is continuous on its domain. So it's continuous on, and the domain is for x less or equal than 2. So it's continuous on the interval negative infinity 2. And here I will keep the interval open, since at this point 2, you're gonna change the expression of f. So be careful, don't include the 2 in your interval. because here you're gonna switch. So to the left and to the right of 2, you will have different expressions. You have to treat this point separately, okay? So for the moment, we are sure that this function is continuous on negative infinity to open, okay? The second function, which is 2x, is also continuous on the interval x greater than 2. It means the interval to infinity. Again, here I will keep the interval open at 2 because I have to check at the point x equals 2 separately. Now, we're gonna check for x equals 2. So you want to check the continuity, you have to compute the limit, okay? And the limit of f of x as x approaches 2 can't be computed directly here because you have two different expressions to the left and to the right of 2. So we have to specify if it's 2 plus or 2 minus. So let's start with 2 plus. 2 plus, it means the second expression. 2 plus means that x approaches 2 from the right. It means it's greater than 2. So it's the limit of 2x as x approaches 2 plus, and this limit is 4, because if you replace x by 2 here, you're going to find 4. Now, the limit to the left of 2 is given by the first expression, because 2 minus means x less or equal than 2. So it's the limit as x approaches 2 minus of x squared. And again here, if you replace x by 2, you're going to find 4. What do you conclude? You conclude that the limit as x approaches 2 is 4 because you found the same value for the left and the right side, okay? The one-sided limits are equal, so the limit at 2 exists, and it's equal to 4. Now, also you have to compare this limit to f of 2. To prove the continuity, you have to compute f of 2. F of 2 is given by the first expression because the equality sign appears here, okay? So f of 2 is 2 squared, which is 4. Then 4 here is equal to the limit of f of x as x approaches 2. So this f of 2 is equal to the limit of f of x as x approaches 2. And using the definition of continuity, we conclude that f is continuous at 2, at x equals 2. And here we are completing our set of real numbers because the union of negative infinity to infinity and the point 2 gives you the set of all real numbers. So f is continuous everywhere. F is continuous on R. Okay? And the domain, or you can write that the domain of continuity is R. There is no point of discontinuity for this function. Next, f of x equals 3x plus 2 if x greater or equal than negative 2. It's equal to the constant 2 if x is less than negative 2. Again here, we can say that this first expression, which is linear or polynomial, is continuous on negative 2 infinity. The second function, which is constant, it's also continuous on its domain, which is negative infinity, negative 2. Okay, we keep the intervals open because we have to check at negative 2. The limit of f of x at negative 2 plus as x approaching negative 2 plus is given by the first expression. So we replace x by negative 2. We're going to find negative 6 plus 2, which means negative 4. The second limit here as x approaches negative 2 minus is given by the second expression, which is 2. So here we found two different. So here we found two different one-sided limits. Therefore, we can conclude that the limit at negative 2 does not exist as x approaches negative 2 does not exist. And this point will be a point of discontinuity. Okay, so the domain of continuity of this function the domain of continuity is the set of all real numbers except the point -2. Okay, so there is a discontinuity point at x equals -2, discontinuity for x equals -2. And here we don't have an infinite limit at -2 plus or -2 minus. We have constants. But these two constants here, the one-sided limits, are different, which means that you have a jump. Okay? You have a jump in the graph of f. So if we want to describe the behavior at this point, we're going to say that we have a jump at x equals -2, since the two one-sided limits are different. Okay? There is no vertical asymptote, but we have a jump at x equals -2. Now let's continue. Here for this function we have three different expressions. For x less than 0, for x greater than 0, and for x equals 0. So the first one is continuous on the interval -∞, 0. The third one is continuous on 0, infinity, and here we have only one point which has to be checked, which is x equals 0. So let's compute the limit as x approaches 0 plus of f of x, and here we have to consider the third expression, which is 1 plus x. 1 plus 0 gives 1, so the limit here is 1. The limit at 0 minus, or to the left of 0, is given by the first expression, which is constant, so it's 1. Therefore, the limit at 0 as x approaches 0 is 1. Now, let's check f of 0. But f of 0 is given by the second expression, which is 0. So f of 0 is 0, guys. You have the limit, which is equal to 1, and the value of the function, which is equal to 0. So what happens here? The function is not continuous at 0. So the domain of continuity is equal to R except 0. The function is not continuous at 0 since the limit is not equal to the value of the function. There is a point of discontinuity, which is x equals 0. So discontinuity at 0 at x equals 0. Now, what happens? The limit is defined. It means that the two one-sided limits exist. They are going to the same point. Let's try to illustrate this. It means that from the left it goes here, and from the right it goes here. It goes to the same point. But here, the value of the function is different of this value. It's not equal to this value. Look at here, f of 0 is 0, which means that you have a hole on the graph of f. Okay? So we can conclude that the behavior of the function will be a hole. So there is a hole in the graph of f, so hole at x equals 0. Okay? Because the two limits are defined, they go to the same point, but the value of the function is not equal to this limit at this point. Okay? It's equal to something else. It means that you have a hole there and a solid point somewhere else. Okay? Thank you for your attention, guys, and see you in the next videos.